Alright, here we're looking at section 11.2. We only have two learning targets this section, so first we're going to distinguish between populations and samples, and then we're going to analyze some hypotheses. So the first thing we need to figure out is what is a population and what is a sample. So a population is the collection of all data, such as responses, measurements, or counts that you want information about. So then a sample is a subset or a smaller group of that population. So let's look at this example. So identify the population and the sample, and then describe the sample. So in the United States, a survey of 2,184 adults ages 18 and over found that 1,328 of them own at least one pet. So here we go, let's look at this. So our population consists of the responses of all adults ages 18 and over in the United States, right? So that population would be everybody. So my sample consists of the responses of the 2,184 adults in the survey. Because I was not able to get a response from every adult ages 18 and over in the United States, I had to take a sample of that population. So here we can see this in the diagram that my sample is my subset. It's a piece of the whole big thing. So my sample consists of 1,328 adults who said they own a pet and 856 adults who said they don't own any pets. But this one we're looking at a sample. So now let's go back to part B. To estimate the gasoline mileage of new cars sold in the United States, a consumer advocacy group tests 845 new cars and finds they have an average of 25.1 miles per gallon. So my population would be gasoline mileages of all new cars sold in the United States. So I'm looking at this sample of the 845 that were tested. Again, I can see that I'm testing a smaller piece than everything that is possible. Okay, so if I was to get data on all new cars sold in the United States, that would be my population. But it's a lot harder to get data on populations than it is samples. And we'll talk about this in coming weeks of what makes a good sample, what makes a bad sample, and things that we can look at for there. So now we're going to look at parameters and statistics. So a numerical description of a population characteristic is a parameter, and when I'm dealing with sample characteristics, it's called a statistics. So again, what I was saying is some populations are too large to measure, which when we're dealing with people is often the case. So then we use a statistic, such as our sample mean, to estimate the parameter, which is the population mean. So knowing that the statistic is what we've tested out of our sample, and the parameter would be that out of the entire population. So here's our next example. For all students taking the SAT in a recent year, the mean mathematics score was 514. Is the mean score a parameter or a statistic? And then explain your reasoning. So this mean is based on 514 is based on all students who took it in a recent year. It's a parameter. Since we're dealing with the population, which was everybody, it's my parameter. So now let's look at B. So a survey of 1,060 women ages 20 to 29 in the United States found the standard deviation of their height to be about 2.6 inches. Is this a parameter or a statistic? Well, we know that this is not every woman aged 20 to 29, so I know that this is going to be a sample, so that this data is going to be a statistic, which is what we're told down here. So the standard deviation of heights is a statistic. So if I know that my sample is representative of the population, meaning, we'll talk about this again in the future, but knowing that I have a good representation of everybody, then I can estimate that the standard deviation of all women would be 2.6 inches. So if my sample is a good representation of my population, I can use that statistic to estimate my parameter. So now try this and think about it. First think about, are we looking at the population or am I looking at a sample? And then am I looking at a parameter or a statistic? That can also help us dealing with data. So now we're going to look at hypotheses, right? This is our second learning target for today. So in statistics, a hypothesis is a claim about a characteristic of a population. So here's some examples. Examples always help me. So here's one hypothesis. A drug company claims that patients using its weight loss drug lose an average of 24 pounds in the first 3 months. So they're dealing with a population of people that take the drug, and they're giving you a claim. So our second example, a medical researcher claims that the proportion of U.S. adults living with one or more chronic conditions, such as high blood pressure, is 45%. So again, we're looking at populations or samples, and we're looking at a claim about those. So to analyze that hypothesis, I have to figure out the difference between results that can occur by chance and results that are unlikely to occur by chance, right? So we're kind of using our probability again. So one way to analyze this hypothesis is to perform a simulation. When the results are highly unlikely to occur, the hypothesis is probably false. So let's look at an example of this. So I roll a 6-sided die 5 times and do not get an even number. The probability of this happening is 1/2 to the 5th, right? So we could have found this out because 1/2 of my numbers are odd and 1/2 of them are even. So here is my probability. So I suspect that the die favors odd numbers. The die maker claims the die does not favor odd numbers. What should you conclude when you roll the actual die 50 times? And then here's our first claim. We get 26 odd numbers and then 35 odd numbers. So let's look at A first. So the maker's claim is that the die does not favor odd numbers. So this is just saying that this proportion of odd in the long run is going to be 50%. So if it doesn't favor odd numbers, it's a 50-50 chance. So we'd want to assume that the probability of rolling an odd number is 50%, right? We're going to just make that assumption based on this claim. So I'd simulate the rolling of the die by drawing 200 random samples of size 50 from a population of 50% ones and 50% zeros, right? So we're kind of looking at our success and our failures. So let the population of ones represent the event of rolling an odd number and make a histogram. So here's my histogram. Okay, so again using my relative frequencies, so the proportion of my 50 rolls that result in odd numbers, and then I can see where they kind of fall out. So getting 26 odd numbers in 50 corresponds to my proportion of 26 over 50, which is 0.52. In this simulation, this result had my relative frequency of 0.16, right? So here's my 0.52, and here's my relative frequency. So in most cases, most of my results were close to 0.5, as I can see because they're closer to the middle of my graph. Because this result can occur by chance, I can conclude that this could be true. So that claim that the makers made was likely true because it is pretty clear. So now let's look at part B, rolling 35 odd numbers. So getting 35 odd numbers corresponds to my proportion of 35 over 50, which is 0.70. So in my simulation, this didn't happen, ever. So because getting 35 odd numbers is highly unlikely to occur by chance, right, because I tried this a bunch of times and it's highly unlikely, I can conclude that the maker's claim is most likely false, because they told me that it was a matter of chance, and you're telling me here that you're showing that that's not true. So now here's your monitoring progress. What do you think? How does this change things? What does this information here change on that last example? Think about it. Let's look back at our learning targets. So first thing we had to do was distinguish between populations and samples, and we just need to know that a population is the whole group and a sample is a little part of that group. And then after that we were going to analyze hypotheses. And look in your book because there's another table or two that can help you determine what we're looking at when we're looking at those hypotheses. So now I want you to go ahead and try this homework for 11.2.